Hi everybody. Today we are going to review for chemical reactions and stoichiometry. So I'm going to go through these problems with you. So first let's talk about synthesis reactions. You're going to recognize that there's synthesis if they have two elements by themselves added together. If that's the case, this is a metal and oxygen, which will give you the metal oxide, or you can look at it as two elements, and when you put them together, you're going to make the compound. Remember, when you make a compound, you have to check charges on your periodic table. So sodium is in group 1, so it's +1, and oxygen's in group 16, it's -2. If they do not add up to 0, you cross the charges, so you get Na2O. And then you have to go back and balance your equation. So now that my charges are dealt with, I see I have two sodiums, but I only have one oxygen here. So if I put a 2 in front, that gives me the two oxygens I need for each side of the equation. And now I need a 4 for sodium. Okay, number 2 is very much like number 1. You've got two elements. You're going to put them together to make your compound. So lithium and nitrogen. Once again, check your charges. Lithium is a +1. And then nitrogen is a -3. So when you cross them, you're going to get 3 lithiums for every 1 nitrogen. I'll rewrite that. So Li3N. And then you have to balance your equation. Since you have 2 N's on the left side, you need a 2 here. And then that will give you 6 lithium. All right, so those are pretty straightforward, kind of basic. If you have 2 elements, make your compound. The other ones are ones that you need to memorize. So you need to be able to look at these and see, oh, I'm adding water or I'm adding carbon dioxide. That's one of your big hints that you have a synthesis reaction. And then you need to look on this side and see, is it a metal oxide or is it a non-metal oxide? And you should have your elements colored on your periodic table to tell you metals or nonmetals in case you don't remember. In this case, we have a metal oxide and water. And so you have to memorize that you get a metal hydroxide. So I'm going to bring my metal over, Ca, and hydroxide is OH with a -1 charge. I look up calcium, it's +2. I cross my charges, so that has to be a 2. It is important that you put this whole thing in parentheses because CaOH2, like this, only implies that you have 2 hydrogens, not 2 oxygens, which is not correct. You have 2 of both. And then when you go to balance the equation, you'll see that that actually is a really good thing because now you're already balanced. In the next case, you have magnesium oxide or your metal oxide plus carbon dioxide. And once again, you need to make sure that you memorize that you're going to have the metal carbonate. So your oxygen will just come over and add to CO2 to make CO3. This is -2. This is +2. So you don't have to add any subscripts here either. Now with the nonmetal oxides, you're going to get oxyacids. So remember, the key thing about acids is that you have a hydrogen in front. And to figure out what your anion is going to be, you're going to add the oxygen to your nonmetal oxide. So that will make it SO4, which is sulfate. And sulfate has a -2 charge. Whatever the charge is here, that tells you how many hydrogens you have to have in front. So a -2 means 2 hydrogens. Same thing here. It's a nonmetal oxide in water. So you're going to add your oxygen to get NO3. And then this is a -1 nitrate. So you're going to add your H in front. I'm aware that this one doesn't balance. If that happens on your test, then I will make sure to let you know not to balance it. All right, so that's pretty much it for synthesis reactions. Make sure that you have those memorized. And now let's talk about decomposition reactions. So I'm just going to trash it. All right, so let's go on to decomposition. Again, some memorization here is needed. The first one, hydrogen peroxide, you have to memorize that that breaks down to water and O2 oxygen every time. And then to balance it, you need A2 and A2. That's just something to memorize about decomposition. The next one is a pattern. It is a metal chlorate chlorates will go to chlorides plus O2. So you're going to bring your metal down, chlorides plus O2. So in this case, I'm going to bring over my metal, Rb. I'm going to put it with Cl for my metal chloride, and then I make O2 again, oxygen. When I balance this one, I notice that I have 3 oxygens here and 2 here, so I'm looking for a total of 6. So I will need a 3 here and a 2 here to get my 6 oxygens, and then that requires a 2 in front of the RbCl. Okay, next one. If you have a compound, you're going to split it apart. If it's not something special that you should remember, right, like a chlorate, a carbonate, or hydrogen peroxide, then you have to split them apart into their elements. So magnesium and oxygen. And then this is where it's really important to remember, if you have elements by themselves, Hofbrinkel comes into play. All of these guys come in pairs. They have 2, subscript 2, so oxygen's part of that group. Once you do that, you have to balance your equation. Okay, and then I showed a bunch of people this trick earlier today. This only works for carbonates, but if you are decomposing a carbonate, you can remember that you're always going to get carbon dioxide out of it. If you think of baking soda, it is a carbonate and it bubbles up carbon dioxide when it reacts with vinegar. That's a good visual. A lot of people will remember. And then to figure out what's left, in case you don't remember, just subtract. You have zinc carbonate to start with. You know CO2 comes out. In this case, it's going to always be balanced. So what you're left with after you subtract CO2, the zinc comes down, your carbons cancel because 1 minus 1 is 0. And then 3 minus 2 gives you 1 oxygen. So that is what you're left with. That is your other product. That only works with carbonates, but it's kind of a neat trick. And then your last one is a compound that we do not have a trick for. So that means you're going to separate it into elements. So Al and Cl. And then Cl is part of your Hofbrinkel. So you're going to do a Cl2 there. Then you're going to have to balance it. You've got 3 chlorides here and 2 here. So once again, your target should be 6. So we need a 3 and a 2 and a 2. Okay, so that was the decomposition. Now for combustion reactions. Move up a little bit. So for combustion reactions, you have to remember that you will always make, if you've got a hydrocarbon here, so remember our hydrocarbons are C and H only, and you're adding oxygen. You always make carbon dioxide and water. This is also true for alcohols. So your alcohol has the OH at the end, but also carbon and hydrogen. That will always make CO2 and H2O also. Okay, so remember when you're balancing combustion reactions, you want to balance your carbon first. So since I have 3 on the left, I'm going to put a 3 here. And then that's going to give me 3 carbons, and it's going to give me 6 oxygens because you have to multiply by the subscript. Okay, so 6 oxygens. Then the next thing you should balance is your hydrogen. So over here I have 8. I need 8 here, so if I put a 4, that's going to give me my 8 hydrogens, and then it's going to give me 4 oxygens. Okay, the reason that's important is I want to do oxygen last, and then since these are on the same side, I'm going to add them together at the end. So I have 10 oxygens total here, and I only have 2 over here. So if I multiply this by 5, that's going to give me 10, and then I'm completely balanced for that equation. Okay, now we're going to look at this next one. Once again, I'm going to balance my carbon first, so a 2, and then I have to keep track of my oxygen. So here I have 4 oxygen. Okay, then I'm going to balance my hydrogen. So here I've got 6 hydrogen total. So I want 6 on this side, so I really need a 3 here. That's going to get my hydrogen taken care of, and then I've got 3 oxygen. Okay, so when I add these together, it gives me a total of 7 oxygen. Okay, now remember, this is equivalent. I'm going to go over here and erase this part so you can see this. Okay, so I have 7 oxygen on this entire side, on my product side. So I need 7 on this side. You'll notice that everything's balanced here except for my oxygen. And I have 1 oxygen right here. Plus something equals 7 on this side. So this whole thing right here, I'm going to want this to equal 6, because 1 plus 6 is going to equal 7. Right? I already have this one here. So I want this term to be 6. So I need to add a coefficient to get me 6. So if I put a 3 here, when I multiply, it's going to give me 6. And then I should be balanced for that. So remember, alcohols are a little bit different because they have that extra oxygen over there. So just kind of remember to include that in your final calculation of your oxygen. All right, so now we're going to look at single replacement reactions using your activity series. So you're going to look at your activity series and you're going to look at the element by itself. That one has to be above one of the elements in your compound. In this case, since copper is a metal, I'm going to look at gold here. So copper has to be above gold if it's going to replace it. And it is on your activity series. So your copper is going to kick your gold out by itself. So I'm going to get AU here. And then my copper is going to take its place with chlorine. Now over here, it tells me that I need to assume that copper is a +2 charge. So if this is +2 and that's -1, when I cross them, I'm going to get 2 chlorines here. As you can see, I have 3 chlorines on the other side. So I need to balance this by putting a 3 here to get 6, a 2 here to get 6, and then I need a 2 and a 3 in front of my copper. So don't forget to balance your equation at the end. All right, so this next equation, you're going to look and you're going to see if zinc is above aluminum on your activity series. And I'm not sure if it is. I almost think no. So let's see if I can find an activity series real quick. So I'm going to go to activity series. There's a bunch of different ones. They're pretty similar. They're not all exactly the same. So I needed zinc to be above aluminum, it looks like. So when I look on my activity series, if I zoom in on this one, well, here it goes. I don't really want to watch the YouTube video. Just kidding. There we go. If I zoom in on this one, I see that zinc is not above aluminum. So for this particular reaction here, zinc is not above aluminum. So this would be a no reaction. It's not going to replace it. Okay, so don't be afraid to write no reaction if it's actually true. All right, now let's look at this next one. So we have cobalt and nickel. I'm going to go back to my activity series. That one's cobalt. Cobalt is directly above nickel, so this one will work. So the cobalt will replace the nickel, and that means my nickel will be by itself, and my cobalt will go with chlorine. And then since I don't know the charge of cobalt when I look on my table, it's one of the D block elements, I'm going to assume +2. Chloride is -1, so I will need a 2 here, and then it is already balanced. Now, I'm sorry, I don't know what happened here. These should be double replacement because you've got 2 compounds, you got 2 compounds. And so we learned that that is exactly what the setup is when you have double replacement reactions. So now let's check out the double replacement. You just have to remember to switch your cations. So you're going to get NaCl and Kf. When you check your charges, you will see that it's +1, -1, +1, -1, and everything is already 1, so that one's already balanced. This time we're going to switch the Ca and the Sr. So my Ca is going to go with Cl2. The 2 is because this is +2, and that one's -1. So I'm not just bringing it over. I am checking the charge, but it just happens to be the same. And then my Sr is going to go with my Br. Same thing. This is a +2, and that's a -1. So this is going to be a 2. And then it is already balanced. All right, I'm going to go through these pretty quickly since we already kind of know the procedure. Just make sure you're checking your charges. So in this case, you're going to have NaNO3 plus KCl, and everything's already balanced. In this case, you're going to have your Ca is going to go with your N. And so this will be a 3 and a 2 because of the charges. And then my Li is going to go with my SO4, and this will be a 2 because of the charges. And so then I have a little bit of balancing to do. So if I put a 2 here for my nitrogen, that's going to give me 6 lithium. So if I put a 3 here for my lithium, that's going to give me 3 sulfate. If I put a 3 here for my sulfate, it's going to give me 3 calcium, which is what I need. And then this last one should be H2O, or you can write HOH, either one is fine, and NaCl, and those should already be balanced as well. All right, now we're going to move on to writing word equations really quickly. So the most important thing to remember about word equations is that you need to make sure that you check charges for everything. So remember, this 2 here tells me that lead is +2. It does not tell me the subscript. It tells me the charge of lead. Nitrate is -1. I like to go through and do my charges first. Potassium is +1. Iodide is -1. Potassium is +1. Nitrate is -1. This one, lead again, is +2. And iodide is -1. So when I go to write my equations, I'm going to cross them. So Pb goes with NO3 with a 2 plus Ki, which is already +1 -1. And then I get KNO3. And then I get PBI2. And I see that I have 2 of my iodide here, so I need a 2 here. Then that gives me 2 potassium. I need a 2 here. That gives me 2 nitrate. Now I'm balanced. Next one, aluminum oxide. So +3 and -2. So that is going to be Al2O3. That's going to decompose, and you're going to get aluminum, which is just Al, and oxygen, which is just O2 because of Hofbrinkel. And so I see I need a 3 here to make 6 oxygen, a 2 here to make 6 oxygen, and then that's going to cause me to need 4 aluminum. Okay, so just remember to check your charges. Also remember that elements that are by themselves do not have charges. They are 0, so no need for charges for an element by itself. All right, now we're going to get into the math portion of the study guide. All right, and so this next equation gives us 8Fe plus S8 gives me 8FeS, and it wants to know moles of iron, okay, which is there. And I'm starting with 16 moles of sulfur, which is there. So I'm going to start with what it gives me, 16 moles of S8. And then I'm going to moles of iron, so I'm going to just use my balanced equation. This is just step 2. So when I look here, I see that I have 1 mole of S8, and then I have 8 moles of Fe, because this step is my balanced equation, so I'm using the coefficients that I have. And then when you multiply, you should get 128 moles of Fe. And since that's what it's asking for, that is your answer. Okay, so though, beware, if you start with moles and end with moles, it's pretty easy. You're using your equation. This one's the same thing. So I'm starting with 3 moles of copper, and it wants moles of Ag. So I'm going to use my equation. I see I have 1 mole of copper, and then I find Ag. I have 2 moles of Ag, so that one goes on top. Okay, and I want to make sure that they're crossed. So if moles of Cu is up here, it has to be moles of Cu down here, because that way, if numerator denominator like this, they're going to cancel out. And I'm going to get moles of Ag as my answer. So that's how I know what to put on top and the bottom. So then since these are both on the top, I'm going to multiply. 3 times 2 is 6 moles of Ag. So that's moles to moles, pretty easy. Okay, now let's get down to it. So this one, we are going from grams of glucose 2 grams of glucose from grams of water using the balanced equation for photosynthesis. I'm going to go ahead and give you a disclaimer here that I have already calculated the molar mass for all the things that I need. So I'm going to drop my molar masses in here real quick. Okay, so I know that glucose, if I'm looking for grams of glucose, I'm going to need the molar mass. So I've already calculated it to be 180 grams per mole. And then I know if I'm starting with grams of water, I'm going to need the molar mass for water too. So I've already calculated that as 18.02 grams per mole. Okay, so I'm counting at this point. I'm counting on the fact that you know how to do your molar mass. So I'm going to start with the number and unit given and substance because that's important here. Okay, so if I'm starting with grams of water, I have to divide by my molar mass, which is 18.02 grams of water for every 1 mole of water. Okay, so you can write it like this, or you can just draw a line and write it under there. But according to my mole map, when I go from grams to moles, I have to divide. So I'm going to get 13.87 moles of water. Okay, so that's my step 1. Step 2 allows me to go from what I started with to what I'm trying to find. So I'm going to use my equation. I have 6 moles of water. That goes on the bottom because it's right here. 6 moles of H2O. And I'm trying to go to glucose, which is this. So that is 1 mole of C6H12O6. So when I divide this by 6, I get 2. So my answer, I'm going to drop down here. So I get 2.31 moles of glucose, C6H12O6, because effectively I'm dividing. I'm taking 13.87 times 1 divided by 6 or times 1/6, however you want to do that. And then my last step, since I'm looking for grams, I have to multiply my moles by my molar mass of glucose. So 180 grams for every 1 mole of C6H12O6. And so then when I multiply, I get 416.2 grams of glucose. I used 4 significant figures here because I started with 4 significant figures here. Okay. All right. So now moving on. Let's see what else. Okay. So here it wants us to write the balanced equation first. So you are going to use all the tricks from going through from words to formulas. So check all of your charges. Plus 3 minus 1, plus 3 minus 3, and then plus 1 minus 1. All right, so that's K3PO4 plus AlNO3 is nitrate, and there's 3 of them because I had to cross it. And that's going to produce aluminum phosphate. They're already balanced, so I'm just going to write it down, aluminum and phosphate. And potassium nitrate, again, already balanced, so I'm just going to write it down. And I see that I have 3 nitrates on my left, so I'm going to put a 3 here. That gives me 3 potassiums. And I think everything else is balanced. Perfect. So in this next problem, I'm starting with potassium phosphate, this guy, 1,000 grams of it. So 1,000 grams of K3PO4. Then I want to know how many grams of this I can make. So that's what I'm going to. So my first step, divide by my molar mass. And I've already done my molar mass here. So this is 212.27 grams of K3PO4 for every 1 mole K3PO4. And that gives me 4.71 moles of K3PO4. Okay, so my next step, I'm going to use my equation. So I see up here I have a 1. So I have 1 mole of K3PO4. And I'm trying to go to potassium nitrate. Well, that's this guy over here, so I have 3 moles of that. So my next step then is to multiply my answer, 4.71 times 3. And I get 14.13 moles of KNO3. Okay, so I'm not quite done yet because it wants grams. So once I have moles, I'm going to multiply by my molar mass for KNO3, which happens to be 101.1 gram per mole of KNO3. So when I multiply 14.3 times that, I get 1,428. However, someone today pointed out so kindly that I only have one significant figure there because my trailing zeros, there's no decimal. So I technically should write 1,000 grams, even though I know it hurts your heart too, because that's not 1,000. But that just shows you what significant figures kind of do. If I'm really not sure about any of these numbers in my measurement in my lab, I really can't be that much specific, right? That much more specific. If I measured 1,000 grams and I put a decimal after it, then that would mean I have four significant figures, and that means it's really close to 1,000. But if I just put 1,000, it could be 1428 because that would round down. Okay. So this is proper sig figs. I will tell you that I will give you plus or minus a digit. So if you put 1,400 sig figs, so 2 sig figs here, that would be okay. Oh, or 1 sig fig. If you put 3 though, that's really too many. So I'll give you plus or minus a digit. All right, so that's that one. Okay, we're going to move on to the next one. So in this one, we're starting to talk about percent yield. Okay, so when we read through the problem, first we have to write our balanced equation. Now it tells us that slaked lime is produced. So that means this is my product. So CaOH2 or slaked lime is my product. And that is when water reacts with quicklime or CaO. So my water, H2O, is going to react with CaO to form my product. Okay. Now it's telling me that I start with 2,400 grams of my quicklime or CaO. And it says excess water because that means that it's not limiting reactant. Okay. It gives me one value. I don't need to worry about water. And then it tells me that I actually make 2,060 grams of slaked lime, which is this. So this is my actual value. And the reason that's important is because we are doing percent yield. So percent yield is your actual over your theoretical times 100. And that gives you your percent yield. Okay, so I know for sure that down here, 2,060 grams is my actual. That's going to go on top. I have to find my theoretical. So anytime you do math, if you start with a reactant and you go to a product, your answer is your theoretical yield. So I'm going to start with 2,400 grams of CaO, divide by the molar mass, which is 56.1 gram per mole. So that gives me 42.8 moles of CaO. Okay, now I realize in my equation, since it's already balanced, I have 1 mole of CaO to 1 mole of CaOH2. It is important that you show me this step because this shows me that you understand that I can't just willy-nilly change my substance. I have to show you how I'm doing that. Okay, so even though my number is going to end up being the same, I have to show you how I go from CaO to CaOH2. Okay, so now that I have moles of this, my last step to find grams, because that's what I need in my percent yield calculation, is going to multiply by my molar mass of CaOH2, which is 74.12 grams per mole. So when I do my math, I get 3,171 grams if I round to 4 sig figs. So I'm going to put that, that's my theoretical yield. So 3,171 grams and then times 100 is going to give me 65%. So that is my yield for that problem. Okay. All right, now we're going to move to the next percent yield problem. Okay, in this case, it's talking about the thermite reaction. And it tells me that Fe3O2 is reacted with aluminum to produce Fe and then aluminum oxide. So that is +3 minus 2. So don't forget to cross. So Al2O3. Very good. All right. We have balanced lots of equations today. So I'm going to go ahead and do this one. So this one is a 2. This one is a 4. This one has to be a 3 to give me 6 oxygen. And then that's going to be a 9. Okay, so that is my balanced equation. And then when I keep reading, it tells me that I start with 258 grams of aluminum. That is a reactant. So that's how I know I have to start with that. It reacts with excess rust, which it told me this was rust up here. Okay, that means it's not limiting reactant. I'm just going to start with 258 grams and go to my product. Now, my product, it tells me I'm forming iron. So I'm going to figure out how many grams of iron I'm going to make if I start with 258 grams of aluminum. Okay, and then my percent yield is my actual, which is 464 grams of Fe, because it has to tell me that in the problem. And then I have to find the theoretical before I can multiply by 100. Okay, so I'm going to start with 258 grams of Al, okay, because that's what it tells me in the problem. I'm going to divide by my molar mass of Al, which I looked up on the periodic table to be 26.98 grams per mole. That's going to give me 9.56 moles of Al. Okay, then I have to use my equation to go to iron. So my equation says I have 4 moles of just Al right here, and I'm going to 9 moles of Fe right here. Okay, so when I do my math, I get 21.5 moles of Fe. So because percent yield is in grams, I'm going to multiply by my molar mass of iron, which is 55.85 grams per mole from the periodic table, and I get 1,202 grams for 4 sig figs. Okay, I guess we probably should use 3 here, so you could go to 1,200. Okay, when I did my math, I used 1,202. Okay, so you're going to divide here, and you should get around 38% for your percent yield. All right. All right, we're moving and grooving. So now we've got to look at limiting reactant problems and excess reactant. Okay, so this one gives you your equation, and we know immediately that it's a limiting reactant because it gives us 2 starting amounts. It gives us the amount of each of our reactants. So that means I'm going to have 2 problems here at least. So I have to start with 13.7 grams of C2H2, and then I also have to start with 18.5 grams of O2. Okay, automatically, I already know that. Now, let's see what it's asking me to find. I like to continue reading because I could pick either product to go to for limiting reactant to see which one I make the least of. But in this case, it's asking me for the mass of CO2. So I don't need to go to water. That's just wasting my time. Okay, so I'm going to go to CO2 for both of these. Okay, so first step, divide by your molar mass. So I'm going to show it differently this time than I did in the last problem. You can do it either way. 53.5. Just kidding. I looked at the wrong one. It's a little bit big. 26.04. 26.04 grams of C2H2 for 1 mole. And I got 0.526 moles of C2H2. And then I'm going to use my equation to go from 2 moles C2H2 in my balanced equation to 4 moles of CO2. Now, I talked about this in class. If you want to stop right here before going to grams, you can do that and wait and see which one is smaller. Okay, so you can stop at moles if you want, but you have to make sure that you get all the way to the product before you stop. You can't stop here. That is not good because that's not going to tell you the right answer. Okay, so now I'm going to do the same thing. I'm going to go to moles of CO2 from O2. So I have 32 grams of O2. That's my molar mass for every 1 mole of O2. And that gives me 0.58 moles of O2. And then using my equation, I have 5 moles of O2 for every 4 moles of CO2. Okay, so I end up with 0.4625 moles of CO2. So when I compare my mole amounts of my product here, I see that this one is smaller. So really, I can just go from here. So to find my mass, I'm going to multiply by the molar mass of CO2, which is 44.01 grams per mole. So my theoretical yield here is 20.4 grams of CO2. Okay, so that is how much I can make. You always want to go from the smaller one because you can't make any more than what your limiting reactant will make. So the next question asked here is, what is the limiting reagent or reactant? That would be O2. So I just go from what my answer is. I go all the way back to the beginning. What substance was that? O2 is limiting. Okay, so if it asks me, that's what my answer is. Okay, let's look at this one. This one, it tells me that I am heating together NH4Cl with CaOH2, and I can make NH3, and then it tells me I also make CaCl2 and H2O. So those are 2 products also, 2 more products. H2O. All right. It tells me I start with 33 grams each of this and this. So if I start with two amounts, right, that is limiting reactant. And it wants to know how many grams of this will form. So this is what I'm looking for. So I'm going to go from each of my starting amounts to that. So 33 grams of NH4Cl divided by my molar mass. This one's the 53.5 grams per mole. So I get 0.617 moles of NH4Cl. All right, I'm going to take this one, go ahead and take this one to my product. So, and I did not even balance my equation. Gosh, what's wrong with me? So sometimes I get into the stoichiometry and realize, oh, wait a second, I didn't do that. So I've got 2 Cl's here. I need 2 here. And that's going to give me 2 nitrogens, which means I need 2 here. That gives me 8, 9, 10 hydrogens. And I have 6 over here. So I need 4 more. And that gives me 2. Okay, yeah, so that's it. Okay, so I have 2 moles of NH4Cl. And I'm going to NH3, so I have 2 moles of NH3. So I literally have the same thing, 0.617 moles of NH3. And I'm going to stop here for a second. I'm going to do the other one. So I'm going to say I've got 33 grams of, what was the other thing? CaOH2. So when I divide by that molar mass, that is 74.12 grams per mole. And then that gives me 0.445 moles of CaOH2. And then for my equation, I have 1 mole of CaOH2 for every 2 moles of NH3. So this time I'm multiplying by 2. And so I actually get 0.890 moles of NH3. So immediately I see that this one is smaller. So this is the one I have to go with. Since I'm looking for grams, my last step is to multiply by the molar mass of this, which is 17.04 grams per mole. So I end up with 10.5 grams of NH3. So here, once I identify my smaller mole amount of my product, I can just go from the smaller one to my grams. I don't have to do both. It just saves a little bit of time. I mean, you can do both and you'll still be able to figure it out. but it just saves you a little time. So now I need to figure out, because it's asking me more questions, what is the limiting reactant or reagent? So if this is my correct product, I go back and I see what I started with. So NH4Cl is limiting. Okay. It really does not like when I write fast. Okay. So now the next question asks, which reactant remains in excess? Well, if this one's your limiting, then your other one has to be your excess. This one's your excess. Okay. So when you are doing any problem, once you figure out what your limiting reactant is, you have to go from that to anything else. Okay. So when you're doing how much excess you have, you are going to go from your limiting reactant to your other reactant. So because I'm running out of room, I'm going to erase the problem that did not matter. This one did not matter to me because it was not the correct one. Now, you don't have to erase yours, but I have no room. So I am erasing mine. All right, so now I'm going to start with my limiting reactant, this guy. But instead of going to a product, I'm going to go here. And when I do that, it's going to tell me if I start with this much limiting, it's going to tell me how many grams of this I actually use in my reaction. So I know that my first step is to go from grams to moles. So since I already did that right here, I'm going to start here. 0.617 moles of NH4Cl. Since that's my limiting, that's where I'm going to start. It just saves me a little bit of time since I already wrote it down. So now my next step is where I go from moles of this. It's getting slow on me. To moles of my other reactant, which is CaOH2. Okay. So I'm essentially dividing by 2. And when I do that, I get 0.3085 or 309 moles of CaOH2. Now, if you did not erase your problem before, you realize that you already have the molar mass of this guy in the problem, the one that I just erased. So I'm going to multiply by that molar mass, which was 74.12 grams per mole. And that's going to give me grams of CaOH2. And this is how much I actually used in the reaction. So when I do this, when I go from the limiting reactant to another reactant, it tells me how much I actually used. So in this case, this was 22.87 grams of calcium hydroxide. That's what I actually used. Now, to figure out how much I have left over, which is your excess, you have to go back to your problem. How much did I start with? 33 grams. So I'm going to go over here because I'm running out of room. 33 grams is how much I started with. And I just figured out that I used 22.88. Oh, it really doesn't like me. 87. And I'm going to subtract that. So when I subtract how much I used from how much I started with, I get 0.1 grams, and that is my excess. Reactant. Okay, so you subtract how much you use from what you start with in the problem. And that's as easy as it gets. Okay, so we're going to trash this and look at our last problem. Okay, this gives us a whole bunch of information. It tells us nitrogen monoxide. Since I have a prefix, I don't need to look at charges. That is the only time I don't. It is formed primarily in car engines, and it can react with oxygen to form sweet gaseous nitrogen dioxide. So I'm reacting this with oxygen, and I'm going to form nitrogen dioxide. There's my prefix again. Awesome. So NO2. Okay, now I have to balance this. At least I'm assuming so. So I have 3 over here, so I need a 2. That gives me 4 oxygens, 2 nitrogens. Put a 2 over here, 2 nitrogens, 4 oxygens, and I'm done. Now I'm going to keep reading. It says nitrogen dioxide forms nitric acid when it comes in contact with water. So I know that NO2 is going to make nitric acid, which I happen to know is HNO3. I know you guys don't necessarily know that. Plus water. That's the reaction that makes that happen. And cool. Then it keeps going and it says if I have 3.13 grams of nitrogen monoxide, so that's over here, 3.13 grams, reacts with 4.16 grams of oxygen. And it wants to know how much nitrogen dioxide will form. So grams of this. Cool. And then it says what is limiting and what is in excess. So literally, I don't even need this. Just extra information. Cool. You never know. So you just got to keep reading the problem. Okay, so once again, it's giving me 2 starting amounts. So I'm going to start with each and go to NO2. So 3.13 grams of NO. I have my molar mass already done, so I have 30 grams of NO for every 1 mole. And that gives me 0.104 moles of NO. Now I've got to go to my product. So I've got 2 moles of NO to 2 moles of NO2. So again, I have 0.104 moles of NO2. All right, now I'm going to go ahead and do my other one, and then I'll come back if I need to do grams. So 4.16 grams of O2. Molar mass is 32 grams of O2 for every 1 mole of O2. Okay, so that gives me 0.13 moles of O2. And then this time when I use my equation, I say I have 1 mole of O2 for 2 moles of NO2. And so I'm going to multiply that by 2. So I get 0.26 moles of NO2. Well, this one's my smaller one, so this one is not it. So this one I'm going to take to grams by multiplying by my molar mass, which is 46.01 grams for every 1 mole. And then my answer ends up being 4.79 grams of NO2. All right, so that is my answer for how much nitrogen dioxide will form. Okay, now I'm going to go back. What did I start with? NO. So that answers my next question. NO is limiting. Woohoo. Now it wants to know how much excess do I have. So one more time, we're going to start with our limiting reactant. So, and I'm going to erase this because once again, I'm out of room. So I'm going to erase the bottom. You would not have to do this if you have more room than me. Okay, I'm going to go ahead and switch colors to make it a little easier to tell the difference. Okay, so now I'm going to start with my limiting reactant. And I'm going to go ahead and start with, I'm going to go ahead and start with my mole amount because my first step would be dividing by the molar mass of this anyway. So I'm going to start with 0.104 moles of NO just to save me time. And so remember, this time I'm going to O2. So I have 1 mole, just kidding, it's 2. 2 moles of NO up here for every 1 mole of O2. So I'm going to divide that by 2, and I get 0.052 moles of O2. And then to find my mass, I'm going to multiply by my molar mass of O2, which is 32 grams for every 1 mole. And then that gives me 1.66 grams of O2. Now remember, when I start with limiting and I go to my other reactant, this is how much I use up. This is used in my reaction. So to figure out how much I have extra, which is what excess means, I go back to my problem. How much oxygen did I start with? 4.16 grams. And then I'm going to subtract 1.66 grams because that's how much I used. And then I get a whopping 2.50 grams of O2 in excess. Woohoo! And we are done. That is all, folks. Hope this was helpful.